Okay, this is a typical problem you'd see out of a textbook for exponential equations. And you can kind of ignore this and just look at the table. So if you look at the table here, and I'm going to pull up some stuff we can write with here. But if we look at this table, so if you look at that thing and you look at it and it goes carbon dioxide, ppm stands for parts per million. So it's talking about the parts per million in the atmosphere of carbon dioxide. Well, if you look at the years, you've got 1990, then 2000, then 2075, then 2175. I mean, you're talking about way beyond. Like right now when I'm making this video is 2023. I mean, that's my current year. Well, holy cow. You cannot, we don't know what's going on here. So we're just going to have to kind of ignore that for the most part and look at our, because that is extrapolated data. That is way into the future. We're going to have to be real careful how we use that data because they're basing it on a model we may not know. So what you want to do is just focus on the years. So I'm assuming that this was actual data that they collected, and this was actual data that they collected. And so it wants us to find the exponential function that gives the amount of carbon dioxide y in the year x. Well, exponential, if we assume it's growing exponentially, that's a big assumption, but we're going to assume it. This is the formula for any exponential growth model. Y equals P, which stands for, P stands for the initial amount. E stands for the number 2.71, blah, 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 blah. We could go into that, but we won't. But it's kind of like pi. R stands for our yearly rate of growth or hourly, whatever we're doing. In this case, it's yearly. And T is time in years. So if we want a formula for this, if we start in 1990, so what we would have to do, so let's look back here at our graph. And here's the thing. We're going to let 1990 be 0 years. That means 2000 is 10 years after that. And so our equation with the 1990 would be y equals 353 years e to the r times 0. So that's our initial amount. Well, if we go to the next one, which is 10, which is 375, so now y is 375 equals 353 e to the r times 10. And so we could solve this for r to come up with our rate of growth for our specific deal. So what you would do is then divide by 353 to get the r by itself. And so when we do that, we get 1.062 equals e to the r times 10. And again, that decimal keeps going, but I rounded it off to the nearest thousandths there, but good enough. And so what we do then is we would take the natural log of both sides. So the natural log of this, the natural log of this, and what that does is it pops that 10r out front. So we would have 10r e, 10r ln of e equals the other side here, which is ln of 1.06. So I flipped them also, 1.062. And if you notice, if you plug that into a calculator, ln of e is 1, so that's gone. So you'd have 10r equals ln of 1.062. you would divide by 10, and that is going to give us our R value. And if you plug that into a calculator, plug this in right here, you're going to get 0.00602 for your rate of growth for that particular problem. And before I slide this off, so we're going to come up with our function for y, and we're going to estimate the year when the level of carbon dioxide will be double the pre-industrial level of 280. So in the early 1800s, pre-industrial revolution, our carbon dioxide was roughly 280 parts per million in the atmosphere. So we're going to go ahead and calculate that times 2 with our formula here. So here we go. So our formula then is y equals 353, because that was our initial amount, e to the 0.0000602 times t. So that's our model, or x, excuse me. And so that gives us our model. Then 280, if you double that, so 280 times 2, because we want to know when is our carbon dioxide going to be twice that. Well, that'd be 0, that'd be 6, 1, that'd be 560. So 560. So we know 560 equals 353. Okay, so we've got this 560 equals 363 e to the 0.00602 times x, or t, whatever you want to do. And so we're going to go ahead and divide the 353 to get that out of the way. And so whatever that is on this side, and if you divide it, it'd be 1.586. We'll leave it like that. E to the 0.00602 x. And so what's next is you take the natural log of both sides, so that this x pops to the front. Again, anytime you have an x as an exponent, you can natural log both sides, pop that thing out front. And so then you have the natural log of 1.586 equals 0.00602x times ln. Well, ln crosses out, the same thing. So we can end up dividing by 0.00602, 0.00602. And so my years when it will be double is to take the natural log of 1.586 divided by 0.00602. And so what you get is approximately 76.6 years. And so that's from 1990. So you'd add 76.6 years to that from 1990. And we get the year 2066. So in 2066 or 2067, it depends on how you want to round that. We're projecting into the future, so you can't be too accurate because there's not a lot we can do there. But we'd have around 2067, we're going to have twice the amount of carbon dioxide in the atmosphere. And so there you go. That gives you a good prediction of when we have twice the carbon dioxide. based on actual data we have and a model we're predicting, because who knows, maybe it'll be linear. And so let's move on to the next problem. And so the next thing we need to do is just talk about what doubling time means. It says, how long will it take for money in an account to accrues interest at a rate of 3% compounded continuously to be doubled? And so when you do this problem, again, if we just assume that growth is exponential, compounded continuously, we'd use y equals pert, p equals r to the t. Again, it's the same e equals r to the t. It's the same thing we've been doing. But the thing is you would just assume that p is some number. It could be 5, who knows. We're going to start with $5. If it grows at 3%, when will it be $10 is what it's really asking. And so you'd go 10 equals 5e to the 0.03 t. So right there's the formula we're after. And so if you solve this thing, then we divide by 5, and that'd be 2, equals e to the 0.03 t. And the thing is, if you would natural log both sides now, you'd have 0.69 equals 0.03 t ln of e, and the ln of e will cancel out. So you're going to have 0.69 equals 0.03 t. So you divide by 0.03, and t is equal to 0.69 divided by 0.03. Well, we know this thing called the rule of 72, which tells us the doubling time approximately. So 72 divided by 0.03. Or not 0.03, sorry, just 72 divided by 3. Because if it was 0.03, then we'd want 0.72. You'd have to move the decimal over twice. So the rule of 70, what I'm trying to get at is the rule of 72 and the rule of 69 there are the same rule. They just came up with the rule of 72 because it has more divisors than the number 69. And so we can go ahead and calculate it approximately with the rule of 72, or more precisely with the exponential equation. And if you notice, this particular one gives you 23 years. And if you check out 72 divided by 3, you get 24 years. And so there's a year difference between them, so it's not that big of a deal. But that's the rule of 72 versus the actual doubling time using continuous growth with the exponential function. So there you go. And so we got one more problem to deal with, which is this one. According to the U.S. Census Bureau, the world population reached 6 billion during 1999, and it was growing exponentially. By the end of 2010, the population had grown to 6.9 billion. The projected world population T after 2010 is given by this function. Based on the model, what would the population be in 2025? And so in this particular problem, we can just plug the 2025 in, and we started at 2010. And since it was 2025, and 2010 was when we started, that'd be 15 years. So we know F at 15 would equal 6.947 e to the 0.00745 times 15. And so you can plug that in and just get the answer for part A. So that's A. And we'll go ahead and find that. So in 2025, we should expect 7.768 billion people, which is actually pretty close. That's not bad. I think we're a little higher than that, but I'm not sure if we've reached 8 billion people yet or not, but we're getting there pretty quickly. But it's going to taper out. It's not going to be an exponential function. It's going to be a power function. So instead of, we're expecting it to look like this, but in all actuality, it's going to look like this, and it's going to level out. So, I don't like to add to the climate crisis with my mathematics problems, because I don't think it, it just depends on what you want to decide to do with it. Anybody can use math to promote their position in the world. And that's why you learn math, so that you can learn how to not be sucked down a conspiracy theorist perspective. So then part B says, if this trend continues, approximately when will the world population reach 9 billion? So in other words, we just do the exact same thing, but we stick a 9 there. So 6.947 e to the 0.00745 x, or t, whatever you want to do. And we're going to solve that particular equation. And so if you do that, then solve it, you would divide by 6.947. And if you do that, you'd have 1.296 equals e to the 0.00745x. And then you would natural log both sides. Stick that in both of those. And so you'd have natural log of 1.296 equals 0.00745x. And the ln cancels out. So you divide that 0.00745. 0.00745. And so you take that divided by 0.00745, and you get 173.9 years. So about 174 years. So from 2010 to reach 9 billion, you take 2010 plus 174 years. And so we're looking at 2184. Quite a ways into the future for when we reach a 9 billion population. And so maybe our number is not correct here, this 0.0745. And so we'd probably want to look at that. That might be, because maybe we're going to be there sooner than that. I mean, this is a huge assumption here, that percent growth. Because, I would assume we would be there sooner than 2184. But, and that's where you need to start thinking about this stuff. You want to take your brain and go, hey, that seems a long ways in the future. 8 billion, we're at about 8 billion now. Suddenly it's going to take that long to get to 9 billion. Maybe our percent growth is not as much or is higher. Whatever. We need to just think about those type of things. And that's the problem with predicting the future. You can't predict the future. Mathematical models only give us only can go so far and only give us some aspect of what we could see in the future. And so we have to pay attention to what's going on, look at our current climate, look at what's going on in the planet to decide, is this population going to be higher, lower? As crazy as things are, maybe it's going to be zero. Maybe the human population will be zero by next year. You never know. That's the problem with predicting the future. We could have some huge solar burst that destroys all of our continents and our population drops to zero, except for the people that live under the earth. Who knows? Anyway, see you next time.